Well, I think we all realize that there are many instances in which we know some distances among points, and we'd like to know if there's a full set of points that enjoy these distances. And roughly speaking, that's the problem that I want to talk about. So there are many applications. One that was actually briefly mentioned in the prior talk is the molecular conformation problem that motivated me to some extent. So I'm going to talk a bit about distance matrices, just the theory of them, and then talk about the necessary background. I made a slight change in the order here. I think I'll first talk about the necessary graph theory and then about completion problems in general before getting to the punchline, which is what I know in the distance matrix case. And then I'll give some references at the end. Okay, so what's a Euclidean distance matrix? Well, we start with some points in Rn, in Rk. Let's suppose we have n of them. And I'll use the usual notion of distance, Euclidean distance. And so I'll say that the distance between point Pi and Pj is just the Euclidean norm of the difference between Pi and Pj. We can array these distances as a matrix, and that'll be a real n by n matrix. And for convenience, what I'm going to array is not the distances themselves, but the squared distances. This makes the statement of many results easier. So this matrix that we get in this way is, of course, symmetric because the distance from one point to another is the same as the point from the other to the one. It's necessarily non-negative because these are distances. And it's a matrix with zero diagonal because the distance from one point to itself is zero. That's called a hollow matrix. And I'll refer to these as the obvious necessary conditions. Of course, there's another condition, and that's the triangle inequality, which I might have included in this list, but I think it's not necessary. So I'll call D a distance matrix. I should say Euclidean distance matrix, and in fact, I'll use that most of the time. But distance matrix for short, precisely when such a collection of points exists that explains the entries of the matrix. Now, the real space that we're working in is called the embedding dimension. And many things that I'll say can be extended to a fixed embedding dimension. But as was noted in the last talk, in general, things become much more subtle when you worry about the embedding dimension. Two of really good references, which I'll give at the end, the book by Blumenthal, which is now rather old and frankly needs to be replaced. So if somebody's thinking about it, I think it would be a good idea to write a new book on distance matrices. And of course, the papers by Schoenberg provide a lot of the foundation about distance matrices. So how do I recognize, if you hand me a full matrix, how do I recognize if it's a Euclidean distance matrix? So first of all, it has to meet the obvious necessary conditions I mentioned. But then in addition, one criterion that can be used is a quadratic form of the matrix D, orthogonal complement of the vector of ones, which I'll refer to as E. Now, there's a choice here. If I want the distances to be strict, in other words, the points to be distinct, then I could say negative definite. And if I want the points, want to allow the possibility of coincidence among the points, then negative semi-definite is appropriate. So another way of saying the same thing is via the Schur complement of the upper left 2x2 block in the bordered matrix, in which I put D in the lower right and then border with the vector of ones along the top, the vector of ones down the left side, and a 0, of course, in the 1, 1 position. If I take the Schur complement of the 0, 1, 1, 0 matrix in the upper left of this matrix, then another way of saying the same thing is that the resulting Schur complement should be negative definite if I want to have proper distances. Okay, in fact, the rank of the Schur complement is precisely the embedding dimension for the points, if of course D is a Euclidean distance matrix. Now, there are other approaches to recognition, some of them Monique mentioned, but from an algebraic point of view, it's also possible to look at a certain kind of linear transformation that necessarily maps the Euclidean distance matrices to and back from the positive definite matrices. I won't go into this in any detail because I'm not going to use it in this talk, but there's another way of looking at this. This transformation, of course, transfers the question to checking for positive definiteness, and it will produce a set of points when the matrix is a Euclidean distance matrix. In other words, it'll produce a set of realizing points via a Graham matrix. Okay, now please indulge me in talking a bit about some graph theoretic background, which I will need. So I'm going to talk about undirected graphs on vertices and edges. So the vertices here are noted by circles, the edges by lines. Here's an example with 6 vertices and 7 edges, and it happens to be connected, which means that I can get from any vertex to any other vertex via a path in the graph. So a path is simply a very simple graph in which all the points lie on a single line. A tree is a little more general in that I have a connected graph on n vertices with precisely n-1 edges. And so an example of a tree is given there. A cycle is simply the path with one more edge that connects the 2 terminal vertices of the path. And I'll say that something is a chord of a cycle if it's simply a shortcut across the cycle. In this case, the chord is denoted by a dotted line. Okay, now a very important kind of graph that comes up in this business is what's called a chordal graph. A chordal graph is a connected, undirected graph such that every time there's a cycle in the graph of length 4 or more, there is a chord of that cycle. So for example, this graph is chordal because it has a chord cutting across the 4 cycle. And this one is not because there's no chord in that cycle. Every tree is naturally chordal because there are no cycles, and so the definition is vacuously satisfied. Now, a clique is simply a complete graph that perhaps occurs as a subgraph of a larger graph. So here's an example of K5. Notice that there are 5 vertices and all the possible edges occur. That is, every vertex has degree 4. Now, a clique sum of 2 graphs is simply the following. Suppose I have 2 graphs and each has a clique of a given, denote a clique of size 3. And if I simply identify the vertices of those cliques in any way you like, I get a new graph with fewer than the union of the vertices because I've identified the black vertices, and the new graph is called a clique sum of the 2 prior graphs, okay? Now, the interesting thing is that a graph is chordal. I've already given the definition, but here's a useful characterization. It's chordal if and only if it's a sequential clique sum of cliques. So what you should imagine is that you have a big pile of cliques sitting over here, and you pick out 2 cliques, and you make a clique sum of those 2 cliques by identifying a subclique of each. And then you continue the process. You pick out a new graph from your pile of cliques, and you clique sum that new graph with the graph you have so far. You continue that process, and what you will get is a chordal graph. And in fact, every chordal graph can be produced in that manner. Now, a corollary to this, and a very important one, is that if a graph is chordal, then you can add edges to it one at a time in such a way so that the resulting sequence of graphs satisfies the property that each successive graph is itself chordal, and the final graph is the complete graph. So I can complete my graph to a complete graph via a sequence of chordal graphs. So I start with a chordal graph, and I have a sequence of chordal graphs ending with the complete graph. Now, one of the first ways in which chordality originated was that people realized that if I do Gaussian elimination on a symmetric positive definite matrix which has zeros, then I can perform the calculations in an order so that I never destroy any zero that I have, okay? And that's exactly because of this corollary. I can order things properly. Now, of course, this requires an order in which I add the edges, okay? And that order is not unique. In general, there are at least two such orders, and typically there are several such orders in which I can add the missing edges and maintain chordality. So now let me talk about matrix completion problems in general. And there, the basic object is that I need a property that I'm interested in. I'll call it script P. So script P is simply some matrix property. Here's a list of famous ones: being positive definite, having a particular rank, being a Euclidean distance matrix, being a stable matrix, whatever you like. There's lots and lots of properties that people naturally study. Now, for square matrices, and so let me confine myself to that case, although there's certainly a non-square version of all of this, P is said to be an inherited property if P has the property that every principal submatrix of a matrix with property P also has property P. For example, this is a feature of positive definiteness. If I have a positive definite matrix, every principal submatrix must be positive definite. If I'm totally positive, that is, all the minors are positive, then every principal submatrix will be totally positive, even in the non-square case, any submatrix. And of course, Euclidean distance matrices. If I look at a principal submatrix of a Euclidean distance matrix, I must have another Euclidean distance matrix. Okay, now, I want to define a notion, and I don't know if this is the best name, but I've used real polynomially describable to say that the property P is real polynomially describable if it can be viewed in the space of all matrices as a semi-algebraic set. So I should have said Mn of R or Mn of C here, I guess, instead of Rn and Cn. So I can describe this property by a finite list of polynomial inequalities and perhaps equalities with the proper ands and ors in this list. So this is an idea from real algebraic geometry, which Monique also mentioned, and a set is called semi-algebraic if I can describe it by a finite list of these polynomial inequalities and equalities. Okay, now an interesting fact is, well, fact I don't know, let me say assertion, any property that anyone cares about is real polynomially describable. In a paper with Leal Duarte, we went to some lengths to think of every property that anyone has ever studied in earnest. Now, this doesn't mean that you can't make up a matrix property that's not real polynomially describable, but all the ones that people are interested in are real polynomially describable. Okay, so in particular, Euclidean distance matrices are real polynomially describable. Okay, so an important issue. Now, another key ingredient in matrix completion problems is the notion of a partial matrix. What is a partial matrix? Well, some of the entries are specified. Okay, we know those, they are fixed, we can't change them, while the other entries are free to be chosen. Okay, so here's a simple example, and I've indicated the free entries or the unspecified entries with question marks, and then the specified entries are given. Now, in most square problems, it's natural to assume that the diagonal entries are specified, okay? So as in this example, I've specified the diagonal entries, and some of the off-diagonal entries and the remaining off-diagonal entries are free to be chosen. And in this example, I have symmetry just as we would in the positive definite problem or the Euclidean distance matrix problem or others. What's a completion of a partial matrix? Well, it's some resulting in a good old conventional matrix. So for example, in this problem, if I make the question marks -1 and 1, I get an ordinary matrix, and that's called a completion of my given matrix. Now, the P completion problems, remember P was our property, simply asks which partial matrices have a completion with property P, okay? A natural question, and I'll talk about that in the distance case. Now, if P is an inherited property, it is of course necessary that the partial matrix be what we call partial P, i.e. all the fully specified principal submatrices themselves have property P. Of course, inherited means that this is a necessary condition, so I may as well assume that when I talk about partial matrices if I'm interested in the P completion problem. Now, this necessary condition may or may not be sufficient, okay? It simply depends on the pattern of the specified entries. Typically, in problems, for some patterns of specified entries, I don't need to know anything else. And for other patterns, I do need additional conditions. So I want to say a little bit about that. So what's the pattern? The pattern is simply the arrangement of the specified and unspecified entries. So for example, the example we had before has this pattern where I've indicated dots for the diagonal entries, X's for the specified off-diagonal entries, and question marks for the remaining entries. Now, in the case of combinatorially symmetric patterns, I can describe the pattern of the specified entries with an undirected graph. And by that, I simply mean the following. The ij entry, if the ij entry is specified, then I have an edge in the graph between vertex I and vertex j. And if it's not specified, I have no edge. So this is simply a graph which describes the positions of the specified entries. And if I'm assuming the diagonal entries are specified, I won't bother taking that into account in the graph. So for example, in the example we've been discussing, here's the graph of the specified entries. Now, an important fact is the following, and this is a fact that comes very nicely from real algebraic geometry. If P is an RPD property, real polynomially describable, then for any fixed pattern, you specify the pattern in advance for specified entries, then the P-completable partial matrices form themselves a semi-algebraic set in the lower dimensional space in which we're working, namely the space in which I have a variable for each of the specified entries and not for the unspecified entries, okay? So there, this set is semi-algebraic, so a very nice fact. What does this mean? That means that P-completability may be checked via finitely many polynomial inequalities. In other words, we fix a pattern, you hand me a partial matrix, there are some polynomial inequalities, such that if they're satisfied in the specified entries of that partial matrix, then that partial matrix will have a P completion, okay? This assumes that P is RPD, but I've already mentioned that virtually every property is. Now, these inequalities may not be easy to find, okay? There are some ways that can do it in small enough cases where the feasibility is not too bad, but in general, it's hard to say what these polynomial inequalities are. If we could, of course, then any completion problem you might be interested in would have a nice simple solution. And sadly, that's not the case. Or maybe, as Henry put it, maybe happily that's not the case because we have hard problems, and so nobody's going to put us out of work right away. Okay. By the way, let me comment a little further. There's very few cases, but there are a few in which, of properties for which one can always find those conditions. For example, the M matrix completion problem is one that's fairly simple, but there are a couple of others. One was in the PhD thesis of my student Shala Nazarazer, for example. So sometimes, given the property and the pattern, if the property is inherited, then the condition of being inherited is all you need to know. In other words, no more than being partial P is necessary. Notice that being partial P is going to be a polynomial property, okay, because we check the specified principal submatrices. I call these P-completable patterns, and it's important to understand those. When do we only need to know that for which patterns do we only need to know that being partial P is enough to know that we have a P completion? So, by the way, let me notice here, last summer in the REU program that I run each summer, we were looking at totally positive completions, which is a problem that's still got lots to do on it. And we found that, okay, total positivity is a polynomially checkable property, all right, but the property of being partially TP is not, in general, polynomially checkable. It depends a lot on the pattern, and we're still trying to understand, what about the pattern makes it polynomially checkable, and this is an interesting problem by itself. So even though being partial P is certainly polynomially checkable, it may be that it's still a difficult problem. Okay, so P-completable patterns are an important idea. So everything I've said so far, I've said in the sort of combinatorially symmetric case, and sometimes the symmetric case, but pretty much all of this can be generalized to properties that are not combinatorially symmetric, may involve non-square matrices, and so these ideas can be extended further. Okay, a good example is total positivity, in which the matrix need not be square, but still these ideas extend fairly nicely. Okay, now let me just close this sort of lengthy introduction, sort of background, a primer on matrix completion problems in general, with the classical result that Henry referred to. I also had two visitors at the time, Bob Groen and Eduardo Sa, and we settled the P-completable problem for the property positive definite. In other words, which are the patterns for which only knowing that you're partial positive definite is enough to know that there's a positive definite completion. And the answers given here, every partial positive definite matrix, the graph of whose specified entries is G, has a positive definite completion if and only if G is a chordal graph, which I mentioned before. Chordal is not so difficult to check, so that's a nice result. Now, there's a lot more that can be said here about the positive definite completion problem. There are further results, many nice things to say, but this is not my primary mission, so I will simply go on from here. Okay, now, Euclidean distance matrix completion problem. So the question is, which partial matrices have an EDM completion? Okay, some do, some don't, of course. Now, EDM is an inherited property, as I mentioned. So in order that I have an EDM completion, every fully specified principal submatrix of a partial matrix must itself be an EDM, i.e., I am forced into talking about partial EDM matrices. And as I mentioned, given the pattern, that may or may not be easy to check, okay? And it's certainly also not always sufficient that I be partial EDM. In other words, things may look locally like distances, but not globally be a subset of distances. Okay, simple example is the following. It was sort of referred to by Monique. So if I have any cycle with 4 or more edges in it, okay, so not have positive weights on all the edges, then I have a partial Euclidean distance matrix. Here's a simple example, okay. I've put on the edges the actual distances, and then I've put in the matrix conventionally the squared distances. Okay, so here's my partial EDM. Each fully specified submatrix is simply 2 by 2, has zeros on the diagonal, and has a positive number off the diagonal. So of course, each fully specified principal submatrix is a Euclidean distance matrix, okay? But it can happen that there's no EDM completion. And in fact, it happens in this case because you'll see quickly that the number 5 is just too big. I can't possibly string out these other numbers, 1, square root of 2, and 1, and actually realize this cycle with Euclidean distances, okay? So this partial EDM has no EDM completion, okay? And I could do the same thing with other cycles. There's an obvious inequality that has to be satisfied, and I'll talk a little more about it in a bit. But when I look at the largest distance that I want to put on an edge of a cycle, it had better be no more than the sum of the other distances, okay? Otherwise, there's no possibility. It's sort of the generalization of the triangle inequality, if you will. Okay, let's see what happened. Okay, I guess that worked. Okay, I lost my, okay. Similarly, if I have a graph with a long chordless cycle, so for no graph with a long chordless cycle, can partial EDM be sufficient for an EDM completion? Why is that? So if I have a long cycle somewhere, I can put bad data, as I described in the previous slide, on the cycle, and then I can always embed it in a partial EDM for the entire graph, okay? So you'll have to take my word for this. Maybe takes a little bit of proof, but in fact, as long as there's a bad cycle, I can embed it in a partial EDM, and then since that bad cycle has no completion, of course, the entire partial matrix has no completion. So what are the graphs for which partial EDM is sufficient for EDM completion? Okay, so what are the Euclidean distance matrix completable patterns, if you will? Okay, Well, what we've just said is that chordality is necessary, because if I have a long chordless cycle, I have a problem. Okay, I can make up bad data, and so not all partial Euclidean data will work. However, it's also sufficient. Now, to prove that technically takes a bit of work. It can be done using the characterization of Euclidean distance matrices via sure complements that I mentioned in the first section. But the idea is the following, or at least an intuitive. Suppose I have two cliques that overlap in a clique with one distance unspecified in my partial matrix. And I've intended that this be the idea here. So I have a 3 clique here composed of x's and the open vertex, and another clique composed of x's and the blackened vertex, okay? Now, if I'm a partial distance matrix, then both of those must be realizable by actual points giving me a Euclidean distance matrix. So consider any realization of them. That gives me a fixed configuration here, another fixed configuration here, and things are tied down by this overlapping edge. And so this will be a point realizable in space. This will be a point realizable in space. And so there will be a distance that I can put here to make the whole thing realizable in space. Okay, so that's the idea. That's not a proof, but it's gives you a notion why this is true. But let me assure you that one can prove that in the case of two overlapping cliques with one edge missing, that we can always find a value for that edge that gives me a Euclidean distance matrix. That is a EDM completion of that partial matrix, okay? So there are several ways to prove this, actually. Another way is the transformation to the positive definite case. Okay, so recall then that we can complete any chordal graph to a complete graph by adding edges and maintaining chordality. So the overlapping clique case is sufficient because each time I'll have a one variable problem. That is, there will be two cliques that overlap with just one edge missing. And I can solve that problem as just indicated. And so by finding a chordal ordering of the missing edges, I can simply complete my partial Euclidean distance matrix as long as it's chordal. So that means that this condition is necessary and sufficient. So given a graph G, every partial EDM with graph G has an EDM completion if and only if G is chordal. Of course, the necessity we've already mentioned by talking about the cycle case. Well, what about other graphs, non-chordal graphs? Well, for sure, more conditions are necessary because the obvious necessary condition of being partial distance is not sufficient. So we need to know something else. So let me give a further example. This is not the whole story, but at least it's a fair part of the story. Let's go back to the case of simple cycles. So let's suppose I have a cycle here on n vertices and of course with n edges. And let me put distances on Euclidean distances on each of the edges. Then there's what I referred to before, namely a cycle inequality, okay? And that is that the maximum edge distance that I see must be less than or equal to the sum of the other distances, okay? That's clearly a necessary condition. I claim it's also sufficient. Now, it doesn't settle the problem of which dimension you can put this in, but in fact, it's if the cycle condition is met, then there will be a completion. So this condition is necessary for the induced cycles of any non-chordal graph. And you can ask the question then, when is it sufficient? Now, before I sort of indicated that you start with a graph and you ask, what are the finitely many conditions for partial matrices on that graph that ensure that there's a distance matrix completion? Now I'm looking at this a little bit differently. I'm saying, okay, here are some conditions, namely being partial Euclidean distance and meeting the cycle conditions. What are the graphs for which those conditions are necessary and sufficient? Okay. So you can look at this by looking at it one graph at a time, or you can look at it by listing some conditions and saying, what are the graphs for which those conditions are sufficient? Okay. So let's see, did I? Yeah. So Euclidean, being a Euclidean graph, the EDM completable partial matrices can be identified by finitely many polynomial conditions. It's not easy to find out what those conditions are, okay? But for which graphs now are the cycle conditions sufficient, okay? Plus, of course, being a partial Euclidean distance matrix. So you can imagine something with some cliques and some cycles, and certain conditions are met by those objects. Okay, in order to explain what these graphs are, I need a little bit more graph theory that I didn't want to burden you with right at the beginning, but here's the idea. So if I have a graph and I identify a vertex in that graph, here I've identified the blackened vertex, then a vertex partition is the following. I simply look at all the neighbors of my identified vertex. I partition them into two subsets, in this case, 3 and 2. And now I elongate that vertex into an edge, okay? So here I have an edge in place of this vertex, and the neighbors of one of the new vertices are one part of the partition, and the neighbors of the other new vertex are the other vertices of the partition that I had of these. That's called a vertex partition, a sort of topological operation you can perform on a graph. So I'll say that a graph, G2, is built from another graph, G1, if G2 can be obtained from G1 via a finite number, and I require at least one, of vertex partitions, okay? So if I can look around, partition a vertex, then when I'm done, partition another vertex, and so on, the resulting graph that I get, I'll say, is built from the original graph, okay? Notice, by the way, that vertex partitioning has as a special case edge subdivision, okay? So another operation I could have described is subdividing a given edge into two edges by placing a new vertex along the old edge. But that's just a special case of vertex partition, so I need not mention it. Now, a special kind of graph, we've talked about having cliques, we've talked about induced cycles, but another special kind of graph that I need to mention is the notion of a wheel on k vertices, okay? So the wheel on k vertices has k minus 1 vertices in a cycle, and then a central vertex hooked to each of those k minus 1 vertices. So for example, this is the wheel on 6 vertices, W sub 6, okay? So a special kind of graph. Now, here's the theorem. Every partial matrix, the graph of whose specified entries is G, and whose induced cycles satisfy the cycle inequalities, and I should have said here it's implicit, and also which is partial EDM, has an EDM completion if and only if the graph has this graph theoretic property. G can have no induced subgraph that is WK for k greater than or equal to 5, nor can it have a graph that can be built from WK for K greater than or equal to 4, okay? So I don't see wheels, I don't see big wheels, and I don't see things built from wheels on at least 4 vertices, okay? Now, there's a lot of other ways that I can state this graph theoretic condition for the patterns that give me completability with these conditions. But in fact, this can be checked in, I believe, and I didn't find the reference in the end, I believe in linear time. So this is, a useful result conceivably. What about other graphs? Well, I think I'm going to close my story here, but it's still an open question as to how to get the conditions for any graph. By the way, just as it is an open question in the positive definite case, there's certainly more work to be done here. There are probably more interesting results to be stated. Also, an idea that occurred to me during this talk, during the preparation for this talk, is Euclidean distance, of course, is different from other notions of distance that come from other norms besides the 2 norm. And in fact, there are even pre-norms and various kinds of notions of distance that one could hypothesize. And I'm wondering, is the chordal result for the completable patterns, for which notions of distance does that remain the correct result? I suspect it's fairly universal. I don't know the limitations, but it's a good question to try to figure out exactly all the notions of distance that lead to a chordal result. Okay, so let me close with the references, which were made with a different processing system, not my fancy new one. But here, let me just mention some of the references. The chordal result is in a paper of mine from some time ago with Mihai Baconi, who sadly is not still with us, a very smart guy who was a student of mine. Here's the Blumenthal book, which goes back to 53. And let me make a plea. I may be done writing books, I'm not sure, but as far as I know, I may be done. But I really think there needs to be a good new book on distance geometry, distance matrices, and that sort of thing. And if somebody knows of one, please let me know, and that may put me out of my misery. Or if somebody'd like to write one, I'd be happy to be helpful in that project. There's a book by Golumbik, which has most of the basic stuff on chordal graphs in it. And if you want to get into this area, it's a good one to look at. There's a nice paper by Gower on Euclidean, non-Euclidean distance matrices, which is to some extent a follow-on Schoenberg work about distance matrices. This is the paper with Henry and Bob Groen and Marquis de Sá on the positive definite completion problem that I mentioned. Then the cycle completable stuff is in a paper with Brenda Kroschel and a student of ours in the REU program some time ago. And then Pablo Tarazaga and I have also worked on this. I don't know if Pablo made it to the meeting, but in any event, he certainly made a lot of contributions to distance geometry.